All right. So let us begin today's class. And if you recall, in the last class, I started talking about VC dimensions, right? So here, like we talked about a couple of things. So let me take you there. So power. So we want to look at the power of or capacity of models of hypothesis classes. So, for example, if I have a linear classifier, right? So what would be the power or capacity of this model, all right? And if this linear model is restricted to pass through the origin, then what would be its capacity? If it is allowed to be anywhere, right? Then what will be its capacity, and so on, right? Then I'll talk about say different kinds of classifiers today, right? Before giving you a quick recap, because it has been I think 3 days when we discussed this topic. So I'll talk about few kinds of classifiers. So one is called as a threshold classifier, or we also call it the decision stump classifier, right? So that is very important in terms of understanding quite a few concepts, and it is also used as a model in several things that you would do in data mining or machine learning. Right. Then I'll also be looking at say circles, right? Okay, nonlinear classifiers. Then other kinds of classifiers called as interval classifiers or box classifiers, right? And again, I'm talking about these in context of binary class classification problems like this, right? Okay. So we'll try to figure out what is the capacity of these family of models, right? So for that, we need to understand a concept which is called as shattering. So how many points a model can shatter, right? And so for that, we need to understand what is shattering. And then we have this concept of VC dimension, right? Which is the maximum number of points that can be shattered by H. That is the hypothesis class H, right? So this H could be anything, right? So we can accordingly, I mean, we can define it based on what we are trying to do. All right. And then let us look at this. So this we were discussing in the last class. Okay. So I was talking about this particular thing. So let me do a quick. So I'll write down the other classifiers here. Not B. All right. So here, how many parameters I have? I have, yeah, 2 parameters. Here, how many I have? 3, right? And if I now talk about a circle, right? So something like this, centered at this point. So how many? So there'll be like a list, right? Circle, right? So this would be 1, right? Only the radius. Okay, so like this, and you can see that if it is just 2, so these are the number of parameters. So, and we already know that if you have more number of parameters, right, in a model, that model is more complex, or you can say its capacity is more, right? Okay, so that you can see from here, like if my line can pass through any from anywhere in this 2D plane, then it will be able to deal with more different kinds of data sets, right? And pass a linear classifier like this one. So, okay. So if my line, right? So if you see this particular example, let me use a different color so that I can differentiate between what is there and what I want to do. Okay. So suppose you are here. So can you fit a straight line of the form f x w is equal to sine w dot x Okay, dot. Okay. Can you fit this line on this data? Yes or no? I hope you understand what I mean by fitting. Yeah. Fitting means zero training error, like in the context of the problem that I'm discussing, right? So, can you fit a line passing through the origin, any orientation, right? Because this is a family, right? This is a family, right, or a hypothesis class. So this is a hypothesis class, all right? And so is this. So is this hypothesis class straight line passing through the origin fit this data? So let me try some of them, right? So let me try this. Does it fit the data?
No, sir.
No. So suggest me some other orientation. So can I try this? Does this fit the data?
No, sir. We'll have to traverse the line, translate
Yeah.
it.
So anything we take, right, which is passing through the origin is not able to do this, all right? Is not able to fit this given data. So this figure only suggests or tells us that this classifier or this hypothesis class classifier, this hypothesis class of classifiers is more powerful than this, right? Do you understand what I'm saying?
Yes, sir.
So I'm saying that this hypothesis class, the FWXB, which has got 3 parameters in it, right, is more powerful than this one, which has got 2 parameters in this, right? All right. So this is what you need to understand. So every model that you come across, so you'll have to somehow talk about its capacity. One way of looking at it is just see the number of parameters that are involved, but there are issues with that. So there are, like, if you have too many parameters, that doesn't mean that the model uh, is good, right? So we need some other aspects. So we need to look at it from different perspectives, right? So one more perspective that I'm going to give you today is the concept of shattering. All right. So let me take you forward. Okay. So this we discussed last time as well, right? Okay. So this is a this is a model or a hypothesis class with just one parameter, which is the radius of the circle, right? So this is the only parameter, right? Now, if I give you points, so let me try to give you points which are like this. Say, for example, okay, let me try drawing something for you. Okay, all right. So suppose this is my y-axis, this is my x-axis, and I have points. Okay. Okay, so let me do or draw a circle first. So this is a circle of radius b centered at this point, which is, say, 3, 0, right? And I have points which are let me take another color, right? And I have points. All right. Okay, suppose this is my data, the green crosses and the red circles. All right. Now, would it be possible for you to have a circle centered at the origin, which will be able to classify these points, fit this data? Sorry.
No, sir.
Yeah, so let me take a blue color. So whatever be the radius, whether it is this one, or it is this one, or it is this one, or it is even bigger one, right? So you will be able to see that, you are able to see that this data, I cannot fit it using this model, right? So what I have done here is that I have made this model slightly more complex, right? So what I do is, so I introduce another family or another hypothesis class, which is like X, and then I'll call it center, right? And then B, the radius. And this would be equal to what? Sine of, yeah, what? So this is center. So how many parameters here? How many parameters for the center in a 2D space? Yeah, how do you specify a center on a 2, right? 2 and 1 is here, right? So 3. So this now has 3 parameters, right? Here I had only one parameter, all right, with this model which is shown in the picture. So what would be my, so it will be like X, how do I write it? I have to write what? I have to write X1 minus C1. No. What is the equation of a circle? If C is C1, C2, so yeah, plus y1, yeah, x2 minus c2 whole squared is equal to, or minus what? B squared, right? So I'll look at the sign of this. Is it all right? Yeah,
Yes.
please confirm, right? I may make mistakes, all right? So you have to correct me all the time. So all right, so I'll take this. So this is another family, right? Another hypothesis set, hypothesis class, right? Okay, so all right, so you can see that this particular model has more power than this particular model. All right, so is that clear? Okay,
Sir,
so
why
let
did
me
you take
move to the
C1
next.
and C2?
These are the coordinates of the center, say 3 0, right? So C1 is say 3 and C2 is 0.
Okay, okay.
Got it? Yeah, so that's the equation of a circle, right?
Yes,
Okay.
sir, yes. And also that's the signum function, right?
No,
Or you
not
wrote
signum, it's the sine function. Just the sign. If it
sine
is
function.
positive, it is outside the circle. If it is less than 0, it is inside the circle. Yeah?
Okay, sir, okay, thank you.
Yeah. All right. So now let me take you to the next slide. So how do we characterize power? Right? So different machines have different amounts of power, as we have just seen, right? Or machines, when I say machines, so these are learning machines, and you can even call them hypothesis class, right? So trade-off between, okay, more power can model more complex classifiers, right? But might overfit, right? So this is what we have seen. Like if the model is more complex, right? Okay, then it has chances. There are chances that it might overfit. Less power, not going to overfit, but restricted in what the model can do. Say again, if I take the case of a circle centered at this place, right? So at the center, and a circle which can be positioned anywhere, right? Okay. So this is a more simple model as compared to this model, right? All right. So this is a more complex model. But the chances are that since this is more complex, it might overfit. So you always have to do this trade-off between um, power of a model and what? And overfitting, right? So you don't want to do that. Okay, so you don't want your models to overfit. All right, so again I'll bring the concept of Occam's razor. So Occam's razor I discussed in the class. Yeah.
Yes, sir.
So if you have two models, right, with comparable accuracies or comparable performance, right? Comparable is important. Performance. Then you should choose the one which is simpler. And why we choose simpler? Because it has less chances of overfitting. Right? So it is always a trade-off between complexity and overfitting. All right. Okay. So how do we characterize the amount of power? In the literature, power is often called as capacity. Right. So I have introduced capacity, if you recall, SRM, that is structural risk minimization. Right. So there I talked about the capacity, which was indicated by H in that formula. I'll come back to that formula in a while. Right? So this is how we do it. So power, complexity, capacity, flexibility, all have the same meaning, right? Literally. All right. So four terms you should keep in mind: power, right? Okay, capacity, complexity, and what is the fourth one? Flexibility.
Flexibility.
Yeah. Right. So I hope all of you are able to follow what is being discussed. So these are very, very important concepts, and this would help you in a lot of things that you would do later on, right? So you have to, I mean, kind of understand them very, very nicely. Otherwise, you'll get stuck, and you will only be able to appreciate concepts at a superficial level, right? But if you know all of these things, then you can do a lot. I mean, you open up lots of avenues for yourself, right, in terms of learning and several other aspects, right? So understand these concepts nicely. All right, right? So okay, okay, yeah. Let me take you here. So train and test errors. So we already know about these, right? Okay. So let us see this. This is the probability of misclassification, right? R alpha, right? Okay. So okay, let me skip this for a minute, and I'll come back to this. So what I want you to look at is this, right here, right at the bottom. Okay. So what do you see here? So this is my test error, which is nothing but the generalization error that we typically call it. This is my training error, the first term here, right? Okay. Plus there's some term. So what we had in SRM was h by n, comma 1 minus eta by n, something like this. No, by capital N. So anybody can recall the formula? It was this only, right? So it was GE plus is less than equal to upper bound to the generalization error was equal to training error plus some function of phi, some function of capacity, where h is the capacity and eta is the confidence. So now what you see here, right? It's a function of capacity and your confidence, and n is the total number of training data points that you have. So now what you see here,
Sir, it was log eta.
log of 1 minus eta, right?
No, log of eta.
Log of eta, okay, yeah. Ln of eta, I guess. Okay, so it was this, right? So now what you see here at the bottommost, like this formula at the bottom of the slide. So look at the phi term. So you can see that we have given a shape or a form to phi, right? That's what we have given. Okay. And what we are saying now is this, that H is nothing but the VC dimension. So H is nothing but the VC dimension, which is the capacity. So VC dimension is actually a measure of the capacity of models, all right, of classifiers per se, right? And VC dimension is in turn defined in terms of capacity to shatter. So capacity to shatter, so shattering I'll just bring in after this, the concept of shattering, all right? So are you okay up to this point? Yeah. So what we have just done here is that we have just given a form to phi, right? So this phi looks like this. So you can see that this is an increasing function of h, right? Okay. There is nothing new here, and r is the total number of training points that we have. All right. So this is a function of h and your eta. Eta is nothing but the level of confidence that you have in the model. Level of confidence with which you can say that the generalization error would have this upper bound. Okay. So this is the same thing. So I've now introduced VC dimension. VC dimension is nothing but the capacity to shatter, and it is the power of power or capacity or complexity of a particular classifier. All right. So remember structural risk minimization that I've already introduced, right? So okay. So now so how to compute VC dimension H for any model F, right? So that is what is the next question. So for this, what we'll do is we'll take different forms of F, right? And then try to talk about or try to find the VC dimension, right? Or H for this model F, right? So let us go there. Okay. So let me give you some background. Okay, so I'm now going to introduce the concept of shattering. So any questions up to this point? Yeah, any questions? Okay, so if you do not have any questions, so let me introduce the concept of shattering. So again, this is interesting. So machine F can shatter a set of points x1, x2, xr if and only if for every possible training set of the form x1, y1, x2, y2, xr, yr, right? Okay. So when I say x1, y1, right? Okay. So in general, this yi, I mean, so if there are say p classes, right? So this yi can take values, I can take values from 1 to up to p, right? And xi is so suppose there are n points, so I'll call that let me call this yj, and let me call this xi. And there are n points, so I will take a value from 1 to up to capital N. All right. So this is the scenario. So I'm not restricting myself to binary classification anymore, although the examples that will work out will be for binary classification problems, right? So I have p classes and I have n training points, right? And since this is in the supervised setting, so I have a training set of the form. So what I can look at xi, so I take x1, right? Okay, so how many labels I can give it, right? Suppose there is a person who is labeling these points, right? So I give him x1, right? Okay, so this person, in how many ways it can label this point? Yeah.
What do you mean by label, sir? Could you explain that?
So yeah, so suppose I'm doing grading, all right, of students. I have made a software, right, which grades students for a particular course. It assigns grades to students. So suppose the grades are say A, B, C, D, E, right? 5 grades are there. Okay. So now I can assign any of these 5 grades to this particular student X1. In how many ways I can assign a grade to a student? Yeah, 5 ways. Yeah.
Yes, sir.
Okay. Right. So I can
Yes,
do
sir.
it in 5 ways, right? So A, B, C, D, E, say for example, right? So let me remove this. So X1, I can give any of the grades, right? A, B, C, D, E. What about X2? Again, 5, right? Okay. So how many different pairs of student to grades are possible?
Number of students multiplied by 5.
Number of
Yeah.
students into number of grades.
Yeah. So I want a nicer form for this. So you can see here. So if there are R classes, right? Okay. All right. R classes. So it will be raised to power R. Yeah. So something I want in the form of exponent. Okay. Say for example, say I've given here, right? So, okay. So if I have 2 points, so, okay, I have 2 points. One is this, one is this. All right. And there are 2 labels. Okay. So how many ways I can label these points? I can give both the students A grade, right? Okay, so this is A, suppose this is also A, this is A, this is a B, this is B, this is A, and this is what? B. I can give it like this. Yeah. Is it not? Okay, I can give both the, if I had just 2 students and only 2 grades. So how many ways I can assign grades to students?
4.
Yeah, 4. 4 is fine, but how do I say this? 2 raised to power
The
2.
number of grades, number of grades raised to power the number of students.
So suppose now I have 3 grades, A, B, and C, right? And I have 2 students. So in how many ways I can do the grading?
9 base,
Huh?
3 raised to power 2.
3 raised to power 2 or 2 raised to power 3? Yeah. Yeah.
3 raised to power 2.
3 raised to power 2. All of you are sure?
So 2 raised to power 3.
2 raised to power 3. So you have to, I mean, decide among yourself what should be the answer.
There are 2 students and number of possible grade per student is 3.
3. Right?
Yes, sir.
All combinations. Right?
So the total combinations will be 3 into 3, which is 3 square.
Also write down. I mean, somebody is saying 2 raised to power 3, somebody is saying 3 raised to power 2. There is a difference of 1. So what somebody is missing or what somebody is taking extra, so that you have to figure out. Yeah, can you enumerate? So let us enumerate. Okay. So I have 2 students. Sorry. All of you can see this. Let me use a different color. Okay, green. So there are two students, right? Student 1, student 2. Grades A, okay, AB, AC, right? BA, BB, BC, CA, CB, CC. Yeah? Getting it? 3,
Yes, sir.
6,
Yes.
right? So how many? Yeah?
3 raised to 2.
3 raised to power 2. So these are the different ways in which they can be graded. Both A getting A, one getting A, one getting B, BA is different than AB, right? So all of this. So 9, right? Okay. So now let me take you back to something important. Okay. Right. So let me introduce our decision stump. Okay. So basically it applies to one-dimensional points. So right now I'm in for a couple of problems. I'll take one-dimensional data, right? So one-dimensional data is like this. So you have some points on one-dimensional data. These are of one types, and these are, say, suppose this is A grade, this is B grade. Okay, this is how the histogram looks like, and I've drawn this. Okay, so now decision stump is a point or is a threshold. It is also called as a threshold function. It is somewhere. It is some value on the real line such that anything above this or anything to the right of this is A, and anything to the left of this is B. So it is just like the cutoffs for grades that we have, right? So I have this data, so I have to find this theta, right? I have some one-dimensional data and I have to find theta. I've done this. So now I can put this theta anywhere, right, on the real line. All right, I have this freedom to put this data anywhere on this number line. All right, okay, right. So, and again, I'm as I said, I'll only be talking about binary classification problems. That means there will be only two classes, right? So one is plus and the other is negative. All right, so I want to know that this thresholding function, okay, how many points it can shadow. Okay, so let us take 1 point. And here I'll also be introducing the concept of an adversary. Okay, so this adversary, the concept of adversary is again a very, very important concept. Okay, so you should understand this nicely. So what this adversary means, like suppose, as I said, like I'm assigning grades, right? So, or I say plus or minus, right? Grades, I'm the teacher, right? Or I'm the instructor, right? And I can assign any grade to any point or any student, right? Okay, either I can assign a plus or a minus, right? So if I have just one student, say for example, so I can either give him a plus or a minus, right? Now the idea is, can you find a grade cutoff such that whatever your teacher, whatever grade the teacher gives you, you are able to put a theta in such a way that points to the left have negative grades and point to the right of theta have positive grades. Okay, so to understand this, let me take, so I'm talking about 1 point, right, or one student. So suppose the student is here. All right, suppose the student is here. Now the teacher, suppose, gives him a plus, right? So where should I put this theta? Yeah,
Either to the left of it or to the right of it.
Anywhere to the left of this point, right? Suppose I put it here, right? Okay. And suppose now I have the same point, okay, the same student, but the teacher says that I'll give him a negative grade. All right. So now where should I put my theta? I mean,
Sir, could you repeat the question?
Question is that suppose the teacher assigns the student a positive grade, right? So this positive grade, so this particular student, and this is the grade, right? So where should I put theta? To the left of this point or to the right? So you guys said to the left, right? Because that is what is my criteria, right? Okay. Now suppose the teacher says that no, I'll give him a negative grade. So where should be my theta? I mean, it has nothing to do with this case, right? Okay, so I'll put it somewhere here, right? Okay, so what I'm saying is that one point, if I can find a solution for all possible labelings, right? How many are there in this case? 2, right? If I can find a solution or a theta for all possible labelings, then I can say that this particular model, which is the threshold function or the decision stump, can shatter 1 point. All right? Getting this? Okay. So what is an adversary? Adversary is one which can label, do the labeling of data in any way it likes. It is basically, adversary basically means a problem, right? Okay, so I'm not saying that teacher is a problem, right? But in general, what happens? So this adversary will try to make your life difficult. That's what an adversary is. Okay, are you getting this? So it will label the data in such a way that you are not able to find this theta. Okay. All right. So this will not be very clear when we are talking about 1 point. Okay. So let me talk about 2 points. So can this thresholding function theta shatter? So the next question, 2 points. All right. So let me have the number line. Okay. And I'll have 2 points. One is here, one is here. All right. So now there is an adversary. Okay. So say a teacher, right? Okay. Although a teacher is not an adversary, teacher tries to make your life easy, right? Not difficult. All right. So let us say, okay. So what do I do? So suppose I say that I label them plus for both. I give them a plus label to both. So can I find a theta? Yeah, can I find a theta? On the left? Yeah. So suppose here is my theta. Now, let me take the same points, but now adversary says that this is like I shouldn't be giving them plus. So let me give them negative. Okay. All right. So can I now find the theta? So your job is to find theta. My job is to label these points in any way I like. So it's a game, right? So we are playing a game. All right. Okay. And if you are able to find a theta, you win, right? Okay. So here you guys win. What about this case? Second case. Where should be my theta? Can you find a theta?
Should be on the right.
Should be on the right. So let me put it here. All right. So you guys win again. All right. So now let me give you a third situation. Again, the points remain the same. Points don't change, right? Okay. I'm only allowed to change the labelings, right? So now what I do is I say that, okay, this is plus and this is minus. Okay. So where should be my theta?
Sir, it should
Between
be
both of them.
It should be
the middle.
in the not in the middle, anywhere in between, right? It could be here also, right? Not necessarily in the middle. Okay. Okay. So all right. So you guys win again. All right. So now, but I have something up my sleeve, right? Now I say I mark this as negative and this as positive. Now find a theta. We cannot find, right? So I kind of stumped you guys, right? So okay, so you cannot find a solution for this, right?
Sir,
So yeah,
sir, could you explain the concept of an adversary?
and that's what I'm saying. I'm playing the role of adversary here, right? Okay, so I'm
No.
telling you that, okay, so let us play a game. All right, there are 2 points and there are 2 labels, right? And if for each combination of labelings, right, if you can find a theta, right, for all possible labelings, right, you win. And if you can't, then I'll win, right? Okay, so who won in this case? Right?
So I have a doubt.
I won the game, right? Or the adversary won the game. All right.
So I have a doubt.
Yeah.
Excuse me.
Yeah. Please go ahead.
So wasn't the point of shattering that we are able to find a solution or a line that can separate the 2 points? Like
Not
to
separate.
one side?
No. Not separate.
Okay.
It is not about separating. It is about finding a theta such that anything greater than or equal to theta is positive and anything less than theta is negative.
Okay. Yeah.
Right? It is not separating the 2 points. The points are the same, right? Same in the sense that the labels, we have to focus on the labels.
Okay.
All right. So I gave you a bet, right? I laid a bet that if you can find shatter 2 points. So now I'm using the term shattering. So can you shatter 2 points with the thresholding function or the decision stump, right? So the answer is no, right? So you lost the game, and right. Okay. So what I say is that the decision stump, right, or the thresholding function theta is not able to shatter 2 points, although it is able to shatter 1 point. So what I can say is that VC of this theta, model theta, right? It is not a value. Model theta is equal to 1. All right? Because it can shatter just 1 point, as we saw in the previous slide. But it cannot shatter 2 points. So its VC dimension is actually 1. All right? Is that clear? Okay. So now let me take you to the next thing. I have some points, some time, so I'll be able to do that. So have you understood the concept of adversary? So adversary will try to make your life difficult, right? This is what I was discussing. So 2 points that I've done already. So I'll just skip this. Okay. So now let me take you to what are called as the interval classifiers. and then I'll take you to box classifiers. So first of all, try to understand what these are. Right. So an interval classifier is such that inside the interval it is positive and outside the interval it is negative. Like for the decision sum, what was the rule? So if any point any point is to the right of theta, it is right of theta, it is positive, and any point to the left of theta is negative. So now in the case of interval, if a point x belongs to the interval, right, it is positive, and otherwise, or if x does not belong to AB, it is negative. All right. Similarly, I have what are called as box classifiers. So what can you say about these box classifiers? So it is like what do you say? Anything inside the box is positive, and anything outside the box is negative. And also, always you can reverse the roles, right? So I can always say that anything inside is negative and outside is positive, right? So it doesn't matter. All right, in context of what we are discussing. All right. So now, how many points an interval classifier can shatter? Okay. Right. So have you understood what we have to do? So let us play this game. Interval classifiers. Right. So 1 point. So let us begin with 1 point. Right. Okay. So again, you are on the number line, and I have this 1 point. Okay. So what label you want to give it? So let us reverse the role. So you label the point. There are two labels that are possible, plus and minus. Okay. So you label the point. I'll put the interval. All right. So what label you want to give it to this cross? Yeah. Plus. All right. So my model is like this. Anything inside is plus and outside is negative. So what will I do? So have I found a solution? Yes or no?
Yes.
Yes or no?
Yes.
Yes. Okay. So now let me do this. So point is this, and now give the second label, because that's the only option you have right now, right? That would be what? Minus. So again, my job is to find an interval such that points inside the interval are positive and points outside the interval are negative. So what should I do? So let me put this interval.
So you need not put any interval.
No, I can put, I can put the interval anywhere, which does not include this point. That's it. Right?
But if there are no points in that interval, doesn't it lose meaning?
So no. What I have to do with 1 point, I have to make sure that this point is outside the interval. That's it.
Okay.
This is a solution. Getting it? So this is a solution. So I win this game. Right. All right. So now let us take the case of 2 points. Okay. So you want me to play the adversary, or you will play the adversary? So let me use a new blank screen. Okay. So 2 points. So we'll close with this, right? So quickly let us do this. So how many possible labelings? 4. So let the points be here and here. So let us quickly do this. Plus plus for both. So what should be the interval? Yeah.
So in this case, the interval will cover both the points.
Yeah. So I'll be able to find this interval, right? So this is done. Right. So points are same, both negative.
You can put it anywhere ahead.
Anywhere
ahead of it.
anywhere which does not contain any of these 2 points, right?
Yes.
Is this done? Yeah. Now 1 plus 1 negative. Yeah, there's a question, I think. What is this? Sir, is the interval size there? Interval could be anything. I have to just find an interval. Interval size does not matter here. Okay. So now what? Can I find an interval?
Yes, just covering the first point.
Just covering the plus point. So you have to take care of the plus. You have to make it safe, right? Inside this interval. Now, what is the fourth possible labeling?
Minus plus,
Minus plus.
and it should cover the second point, as in the.
It should cover the second point. Irrespective of how close they are on a real line, I can always do this, right? I can always squeeze in an interval between 2 points, right? Okay.
Sir, but I think we cannot do it in the case of 3 points when it's like a plus
No, I have
minus
not
plus.
come to 3 points. I have not come to 3 points. Yeah. Okay. So 2 points. Have we found a solution? Yeah. Yes or no? We have found a solution. All right. So now your job, I'll discuss it in the next class. Your job is to find the VC dimension for interval classifier, right? Okay. So can it do for 3 points, 4 points, 5 points? That is what you have to figure out. Okay. And try to do the same thing for box classifiers. Again, these boxes are not necessarily square. They can be of any shape, right? They can be rectangles also, and in any number of dimensions. So right now we are, for simplicity, we are taking only one-dimensional cases. In the box, you'll have to take two-dimensional stuff, two-dimensional points. But this concept can be generalized to any number of dimensions, right? Okay. So I hope you are getting some idea about the concept of shattering and the concept of VC dimension, and also the concept of and we can link it to the model complexity, model capacity, model flexibility, and then so on. All right. So I'll stop here. Any quick questions I'll be able to answer. So in the next one, yeah. No, it can be anything, rectangle or square. Okay, so you can treat them as different problems also, right? So you can treat them as that my my classifier is just a square or a cube or a hypercube or so on, right? And the other case could be that you take them as rectangles. Okay. Quiz, I'll have to, it would be somewhere next week. As I told you, it will be before Diwali, and I'll give you 1 week's time to work on it. Okay.
Yes, sir.
Marks, I'm doing it. I'm stuck with a couple of very urgent things, so I'm not able to get time, but I'll do that. Okay. I'll do that very, very quickly. All right. So hope you have understood the concept. So I'm closing the meeting. Okay. I'll see you on Wednesday. Work on the interval, VC dimension of interval and box classifier.